Hello everyone. Today I am going to explain the new topic, that is consolidation. Or in this topic I am going to explain all these contents. So from now I will start from the introduction. Compression of a soil. The volume of a soil mass is get decreased when a compressive force applied on it. And the property of a soil due to which a decrease in a volume occur under the compressive force is known as the compressibility of a soil, or we can say compression of a soil. And compression of a soil occur mainly due to the four reasons. The first one is the compression of a solid particle. Second is the compression of water in the voids. Third one is the compression and expulsion of air in the voids. And the next one, expulsion of water in the voids. So the compression of a soil due to the compression of a solid particles is very small. So we can neglect this value. If we will take the water is incompressible because the compression of a water in the voids is very small. So the compression due to the compression of water in the voids is very small, so we can neglect this value also. And we know the air is present only in the partially saturated soil or in dry soil. But in the case of fully saturated soil, only water and solid particles are present. So for case of the fully saturated soil, air is not present. So the compression of a soil due to the compression and expulsion of air in the voids, it is not effective. So we can say for a saturated or a fully saturated soil, the compression of a soil or a volume of a change occur in the soil only due to the expulsion of water in the voids. And that is called a consolidation. So we can define the compression of a saturated soil, and then the steady static pressure is known as the consolidation, and it is entirely due to the expulsion of water from the voids. So during the consolidation, or we can say during the expulsion of water from the voids, the solid particle shift from one position to other position by rolling and sliding. And that's why it is an closure packing. So it is very important to note down during the consolidation, decrease in the volume of soil occur not due to the compression of a solid or water, but due to the shifting of a position of the particles as the water escape. Means during the process of when the water is escaping, the solid particles are shifting from one place to other place, and that's why soil attends a closely packing. And that's why decrease in the volume of occur. So the settlement of a structure. So whenever the volume of change occur in a soil, so whatever the structure which is built on the soil, it gets settled in vertically in downward direction, vertically downward, and that is called the settlement of a structure. So it is very important to study the consolidation characteristics to get the idea about magnitude and the time of settlement for a structure. So the consolidation of a soil deposit can be divided into three stages. And these three stages are initial consolidation, primary consolidation, and then secondary consolidation. So the total settlement of a structure is the summation of immediate settlement, which is mentioned in the figure 1, primary consolidation settlement, and the secondary compression or consolidation settlement. So the immediate or elastic settlement, whatever the settlement occur due to the initial consolidation, is called immediate or elastic settlement. So whenever a load is applied on a partially saturated soil, a decrease in volume occur due to expulsion and compression of air in the voids. A small decrease of volume can be occur due to the compression of solid particles. But water is incompressible, so the compression due to the water in the voids is neglected. So the reduction in the volume occur just after the application of the load is known as the initial consolidation, or directly we can say initial compression. And whatever the settlement occur in the soil or volume change occur in the soil due to initial consolidation is called immediate or elastic settlement. Second is the primary consolidation settlement. So whatever the settlement occur during the primary consolidation is called the primary consolidation settlement. So after the initial consolidation, further reduction in volume occur due to the expulsion of water from the voids. So when a saturated soil subjected a pressure, then initially all the applied pressure is taken by the water as an excess pore water pressure. And we know that water is incompressible compared to the solid particles. So the hydraulic gradient develops and the water start flowing out and decrease in volume occur. And this decrease in the volume of soil is depends upon the permeability of a soil. So you can see in the case of fine grained soil, the primary consolidation occur over a long period or long time. But on the other hand, in the coarse grained soil, primary consolidation occur very quickly due to the high permeability. So by the escaping of water, this excess pore water pressure is transferring into the solid particles and thus forming that's why the effective stress is getting increasing. So at the end of primary consolidation, or we can say at the time of completion of the primary consolidation, all pore water pressure is dissipated into the effective stresses. Third one is the secondary consolidation settlement, or we can say creep. So whatever the settlement occur during the secondary consolidation is called the secondary consolidation settlement or creep. So you can see after the completion of the primary consolidation, again the reduction in the volume continue at a very slow rate even after the excess hydrostatic pressure developed by the applied pressure in the fully dissipated. And this reduction in the volume occur due to the plastic readjustment of the solid particles. And this occurs at a very slow rate. So the total settlement is the summation of immediate or elastic settlement, primary consolidation settlement, and secondary consolidation settlement. So the first stage is the initial consolidation, second stage is the primary consolidation, and the third stage is the secondary consolidation. So wherever in this this lecture, or whenever in coming lecture related to the consolidation, so we talk about the primary consolidation, or we can say directly consolidation. Fundamentals of consolidation. So what are the consolidation? So the compression of saturated soil under the steady static pressure is known as consolidation, and it is entirely due to the expulsion of water from the voids. So the fundamental of consolidation we can easily understand by the spring cylinder model. In the figure 2, a spring cylinder model is shown that consists of a cylinder with a spring of its center and a cylinder fitted with a tight fitting piston having a valve. So let the inside area of the cross section of the cylinder is equal to capital A, and let us assume the piston is weightless. So initially when the no load is applied on the piston, so the spring and the stress in the spring and water are initially free of stress. Means the pour water pressure will be 0 and the load registered by the spring will be 0. So initially when the load P will applied on the piston, so what will happen? All the load taken by the water, because the water is incompressible, so there is no deformation in the spring. So if we'll notice a deformation in the spring, so mean the whatever the load is registered by the spring will be 0, because the load registered by the spring is proportional to the deformation. If the deformation is 0, means spring will not support any load. So at t barabar 0, or we can say initial time, initially the hydrostatic pressure will be P by A, because at this point of time all loaded supported by the water. Or generally we can write P is equal to PS by PW, because whatever the load is applied on the piston, it is registered by the spring and the water. So generally we can write this formula, where PS is the load registered by the spring and PW is the load registered by water. So initially when the load is placed, so PS is 0 and PW is P. And after some time, so what will happen? After some time when we wall is keep open, so water will start escaping out from the cylinder and water will start moving out from the cylinder, and spring will get some deformation. So by the deformation, spring will start sharing some load. Spring will start resisting some load, means it will not be equal to 0. So whatever the load is resisted by the water will get reduced. Means that whatever the pour water pressure which develop in the when the t barabar 0 initially, so now it will decrease. So we can write at this point of time PS is greater than 0 and PW is less than P, where P is the load applied on the piston. So after a very long time, what will happen? When you keep the wall is open, the water is continuously flowing out and the pour water pressure continuously is decreasing, and the deformation of a spring continuously increasing. So the sharing of load by the water is decreasing and sharing of the load by the spring is getting increasing. So after a very long time, what will happen? All the pour water pressure will be dissipated in the form of spring stress. So at this point of time, we can write P is equal to P and PW is equal to 0. So this mechanism or this mechanics of consolidation we can understand in the case of saturated clay. So consider a saturated layer of clay of thickness capital H, that is confined between the two layers of sand, top and bottom, and a total stress in applied, a delta sigma is applied on the top of the sand. So this mechanism we can relate with the spring cylinder model, and because of the soil particles in the saturated clay or soil behaves like a spring, while the water in the voids behaves like a water in the cylinder. So in this case, whatever the stress induced between the solid particles, we call a effective stress. And permeability in a soil controls the flow of water. So here, valve, using the valve we control the flow. So permeability we can relate to the valve, which is mentioned in the previous figure, which is fixed in the piston. And the stress developed in the spring can be related to the stress induced between the solid particles, that is called effective stress. So from the principle of effective stress, we can write, so we can write the total stress is equal to the effective stress plus pour water pressure. So this, so that equation we can write in the form of change. Whatever the change will happen in the total stress will be equal to the change in the effective stress plus change in the pour water pressure. So initially, when the total stress is applied, so all the stress is registered by the water. So initially the pour water pressure will be maximum, is equal to the total stress. So we can write total stress is equal to change in the total stress is equal to the change in the pour water pressure, where the effective stress will be 0, because initially there is no stress induced in the solid particles, so the effective stress will be 0. And after some time, the pour water pressure will start dissipate in the form of effective stress. So the pour water pressure will decrease and effective stress will decrease. Obviously it will be greater than 0. And after a very long time, what will happen when the all pour water pressure will dissipate in the form of effective stress, and pour water pressure will be 0 and that very low at this point of time. So we can write delta is equal to 0 and delta sigma and delta sigma dash, means at a very long time, so all the pour water pressure is converted into the effective stress or dissipated in the form of effective stress. So when effective stress is increasing in the soil, and then volume of soil is decreasing, so that decreasing volume or volume of soil we can write in the form of changing the void ratio. So that decreasing volume we can write in the form of changing the void ratio. Means if the effective stress will increase, then void ratio will decrease. So if we plot a figure between the void ratio and time, so we can get this figure. So if from this figure you can see, by increasing the time, void ratio of soil is decreasing, and we get the final void ratio EF1. So this final void ratio EF, because of the change in the sigma delta sigma, if we will again apply a delta sigma, again a different total stress, then EF value, final void ratio, will come a different value, and that would be less than the previous one. So whatever the total stress will apply in the increment form and again, then void ratio will come a different value. So that thing we can plot in a figure. So whatever the total stress will applied, so we got the sigma 1. When again, why we are saying the, why I am saying the total stress, because the finally at the point of very long time, total stress is converted into the effective stress. So whatever the effective stress is developed in the first case, that is the change delta sigma 1 dash, then we got EF1, where again we applied the delta sigma 2, then we get EF2. Means by increasing the effective stress, the void ratio is continuously decreasing. If we will consider the change in the void ratio, change in the effective stress is small, so we can calculate the slope of this curve. and that slope of this curve is called coefficient of compressibility, which generally we denoted by AV. So we can write AV is equal to delta E divided by delta sigma dash. So we can write somewhere you can write also minus delta E, because the void ratio is continuously decreasing, where the delta sigma dash is the change in the effective stress. And if this graph we plot on the logarithm on the log of sigma effective stress, means you will plot the graph between the void ratio and final void ratio and the log of effective stress, then we will get this curve as a linear for normal consolidated clay. And if we make the if we calculate the slope of this curve, so we can get the value of Cc, that is the compression index. We call a compression index, and we can write E2 E1 minus E2 divided by log sigma 2 dash of 10 minus log sigma 1 on the base of 10. So we can write delta E. So we can write also minus delta E, because the void ratio is continuously decreasing. So don't confuse with that. Okay, and that is called the compression index. So some of the formula we can use to calculate the compression index. So for the undisturbed soil of medium sensitivity, undisturbed soil means which is soil which is placed in the in situ condition. So we can calculate the Cc value when the WL is the liquid limit. We can calculate in the form of by using the initial void ratio, where E0 is the initial void ratio. For remodeled soil of low sensitivity, we can use this formula by using the liquid limit. We can use this formula by using the initial void ratio. Okay, so just remember the compression index is the slope of the curve of E versus log sigma dash, and the AV is the slope of curve E versus sigma dash. Okay, so here I am going to discuss some of the numerical problems. And the question number 1, the void ratio of the soil is 0.55 at an effective normal stress 140 kilopascal. The compression index of the soil is 0.25, means Cc value is given. In order to reduce the void ratio 0.4, an increase in the magnitude of effective total stress in kilopascal should be. So here is the initial void ratio is mentioned, final void ratio is mentioned. So the effective stress is mentioned. So whatever the change in the effective stress, that we have to calculate. So given the Cc value, E0 value, all these values are given. So we can calculate the change in the void ratio. So we can calculate 0.55 minus 0.4. We can get 0.15 by using the formula for Cc, compression index. So all these value, we have Cc value, we have the delta E, we have the sigma dash naught, and so we can calculate the change into effective stress. So we can get this value, and that is 417.35 kilopascal. And the second question, the compression curve E versus sigma dash plot for a certain clayey soil is a straight line. So the question is saying the straight line, so we can use the Cc, can use the formula for Cc, because that formula is valid for the linear curve. Okay, it passes through the point E equal to 1.2 and sigma dash V 50 kilopascal and E equal to 0.6, and the compression index of the soil. So given the initial void ratio 1.2, final 0.6, initially the stress, effective stress 50 kilopascal and sigma dash to 800 kilopascal. So again we can calculate the change in the void ratio. We can get the 0.6 and by using, because all these value we have. So we have the change in the void ratio, we have the sigma 2, we have the sigma 1 dash. So by using this formula we can get the value of Cc, and that is 0.50. So we will discuss some more problems in the coming lecture. Okay, and so these are the reference that I have taken. Okay, thank you.